The CHPC conference today, starting at 4:30. It is my pleasure and privilege to introduce Professor Kasim Mtondi. And just as a brief background, Kasim obtained his doctorate in statistical data mining in 2003 from the University of Leeds. He is a well-rounded multidisciplinary professional. He also holds MSc degrees in statistics, computing, and finance, with many years of experience in teaching and research and consulting across continents. His research interests are in extracting knowledge from multifaceted data, and he has successfully secured and managed many interdisciplinary research projects. He's also a regular presenter at a number of international conferences, a keen promoter of interdisciplinary approach to scientific research, to open data and open science, and his research work focuses mainly on the application of deep learning and other machine learning techniques in interdisciplinary modeling of real-life phenomena within the domain of sustainable development goals. So it's my pleasure, Kasim, to introduce you to the audience, and you will probably explain and detail a little bit more on your topic of presentation. So it's over to you, Kasim.
Thank you very much indeed, Anwar. Many thanks to colleagues at DRISA and at CSIR for inviting me to give this talk. It's interesting that it's continuation of the kind of collaboration we've had over the years, probably going back 3 years. And I'm glad to be here and pleased to meet you guys, although remotely. So I'm going to start straight away sharing my screen. And if you can let me know whether it's you. Can you see my screen, everyone? Hello? Anwar, can you confirm that you can see my screen?
We can see your screen. If you would just mind going to opening the full presentation, please.
Right, okay, thank you.
Perfect, all is in order.
Right, okay, thanks, Rudy. So although this is a keynote speech, it's a joint work with my colleague, Robert Storer, who I believe is also in the audience. And we will be talking to you about automated detection of whiskers in hill-shaded digital elevation models using convolutional neural network. So I'll take you through the outline of the talk. We will look at the background, climate sensitive processes that influence global and regional sea levels. And we will proceed to look at the impact of the sea level rise and its implication on climate change, poverty, and food security. As Anwar mentioned earlier, the focal area of our study is to address real life challenges, and probably some of you who attended yesterday's presentation by Stefan Gillich, he mentioned the application of HPC on artificial intelligence and artificial intelligence on HPC. So this keynote is about implementation. We still go through the 4 steps, which he very eloquently presented yesterday, but we will be focusing on implementation that is addressing real life challenges. So on the background, we'll be looking at the study motivation and a bit about problem area, and we specify research questions and objectives, and then we proceed to tracking the footprints of ice sheets movements, also known as ESCAs. I'll then take you through data sources and our general implementation strategy, and look at a bit of the mechanics of the convolutional neural networks, the architecture, and highlight how that architecture and other parameters actually impinge on the performance of the models. And then we will construct the CNN model and see how we can implement it through our previously developed algorithm, which we named sample measure assess or SMA algorithm. Then we present analysis and do a bit of prediction, and then we'll be drawing conclusions and going back to the objectives and looking at the research paths ahead. So the sea level rising is an issue which affects a lot of people. So over 600 million people live in areas which are categorized as low elevation. So there is a lot of uncertainty around this problem, and what will the future sea level rise be? What impact will it have on the people? And this all because there's very little known about the processes which govern the stability of the levels, the sea level rises. Understanding this process is limited by the fact that it's difficult to access the subglacial zones, which lie hundreds or sometimes thousands of meters beneath. I understand in the Antarctica, this is about 5 kilometers, so it's about 5,000 meters beneath the ice. So one approach to address this uncertainty is to investigate areas where these ice sheets have retreated. That is where the beds can be accessed. And we have, in that sense, we have what are known as ESCAs. These are landforms that record the location and dimensions of former subglacial meltwater channels. And in recent years, they were constrained previously because of low resolution. But recently, we are having very high resolution digital elevation models of glaciated regions, which give us an opportunity to understand this. Manual mapping of these features is difficult because there are large areas occupied by them, and that's why we're proposing an automated approach to mapping. So the proposed approach is a CNN. This is an automated method which will be looking at ESCA locations and facilitating the detailed morphometric study of how they formed. Multiple CNN models are trained, and we validate and test them, and using a specific algorithm, as I mentioned before. This is SMA, and we using positive and negative cases of ESCAs, about 1,041 and 37,000 negative ESCAs. We train the models and then we look at the performance, and the main challenge, which is actually is the issue which relates to computing, is about the replicability of this model. And I'll be coming back to this toward the end of this presentation. Those who are familiar with the machine learning, they know that you can always train a model, you can always feed data, training and validate and get some results, but being able to replicate that model on previously unseen data is the main challenge. So that's one thing that I'll be dwelling on more later on in the presentation. So still on the issue of sea level rises, we know that approximately 10% of the world's population, which is just over 600 million people, live in those low level areas. And they are therefore vulnerable to the impact of sea level rise. So understanding why, how quickly this rise happens is vital to the United Nations Sustainable Development Goals, particularly SDG number 13, which focuses on climate change, SDG number 1, which is on poverty, SDG number 2 on food security. To be perfectly honest, understanding why, how, and how quickly the rise happens is vital to all the 17 SDGs, because the 17 are actually inseparable. They are strongly correlated entities, and it's difficult to isolate one, from the other, because there are very strong interrelationships among them. So one issue which has also been of interest is the temperature rise. Glaciologists and climatologists know that there's been an increase of 1 degree centigrade since 1900, which has resulted into global level rise of up to 20 centimeters. A report by the IPCC predicts that this will rise by 60 to 74 centimeters by the year 2100. So research into sea level changes over the glacial interglacial cycles show that sea level was 5 to 10 higher than it is now. At that time, temperatures were 1 to 2 degrees Celsius warmer than 1900. So again, understanding the nature of the meltwater drainage systems beneath the ice sheets is crucial to understanding their dynamics. And this is one thing that we'll be focusing on in this presentation. So let's look at a bit of a problem area. On the image on the right-hand side, we have the hydrological cycle, which interacts with the glaciers and the groundwater. So you can see clearly that here, get a pointer, the melting water parent to go into the groundwater and then form this hydrological cycle. And on the oceans, you've got the atmosphere-ocean interaction with the ice sheets on the other side, and there's geocentric sea level rising, of course, affected by both the left-hand side and the right-hand side. So this is a graphical illustration of the climate-sensitive processes and components that can influence global and regional sea levels. And as I said before, our understanding of how meltwater interacts with ice under warming climate is limited because we are unable to access the subglacial zones. So one plausible approach is to investigate areas where ice sheets have retreated, which we seek to achieve via an automated mapping of high resolution dams of glaciated data. So using deep learning and imagery data. So Here are examples of ESCAs. The lakes on the surface of the Greenland ice sheet can drain under the ice, affecting ice velocity, and that will deliver water into the sea. Very little is known about how this water moves underneath, and so that's why we can use areas where these have retreated, like a large part of Canada, to better understand how water moved underneath the ice. Now, at this point, I think it's important for me to make it clear that my colleague, Robert, has done an awful lot of work in mapping these ESCAs in that part of Canada. So most of the data, most of the mapping initial investigations, they come from him. Joe goes back to his PhD work. Okay, so measurements of ESCAs can be used to understand how much water and sediment move beneath ice sheets, therefore improving our understanding of how water is likely moving beneath them and providing insights into decision processes. So yes, now we've got high resolution imaging data, which we can use in conjunction with the computing power we have to elicit information or to uncover hidden information in the data attributes. On the right-hand side to the bottom, in the bottom panel is the area where the data came from. And that you can see is a huge area in Canada. Right, again, these are pictorial illustrations of how ESCAs look like. So graphical images taken from the air, and they form the data sources that we will be going through with you this afternoon. It's not the first time that ESCA patterns are being used for this purpose, but ESCA patterns and properties have been used to understand the long-term large-scale behavior of subglacial meltwater during periods of climate warming and ice sheets for many years. However, up to now, there is no systematically quantified ESCA work that is in 3 dimensions, and as we mentioned before, this is because there is a limited availability of, there's been a limited availability of sufficiently high resolution elevation data. Now, with the advent of the dams, we are able now to proceed and carry out this process. So this work, we believe that it takes the first steps towards a systematic morphometric analysis, focusing on automatic detection of ESCAs from processed digital elevation data using convolutional neural network. So motivation, mentioned this earlier, that the motivation is to address real life challenges. Now, I think when it comes to real life challenges, nothing epitomizes that statement than the United Nations Sustainable Development Goals. The 17 do actually epitomize our livelihood, our sustenance, our existence on this planet. I'm sure most of you will have seen the SDGs. On the left-hand side here is an image of the 17 of them. As you can see, number 1, fighting poverty, fighting hunger, improving health, education, gender, it's quite easy to see how each one of these depends on the other. Now, advances in computing power and explosions data generations have triggered data-intensive research across disciplines. And one of the outcomes has been the availability of high-resolution digital models, which we mentioned earlier. And this is for specific. If you want to pin it to one of these, 17 is probably be closely to SDG number 13. But as I mentioned earlier, the effect of climate change, of course, impinges on poverty, impinges on hunger, impinges on clean water, and it affects each one of these, and each one of these affects the other. So we're taking a big data approach and develop an automated process for detecting ESCAs in hill-shaded dams based on convolutional neural networks. So by training CNN to identify these ESCAs based on a training set of images where ESCAs have been manually identified as either present or absent, we aim to be able to identify the locations of these ESCAs over that very large area of Canada, which I showed you earlier on. So we're setting a simple research question. How can automatic detection of ESCAs enhance our understanding of rising sea levels? So the general aim of this work, as I said, is to identify which images have ESCAs and which haven't. So we're making this simple as a binary problem. So we look at an image, has an ESCA, so we know that something happened here. There is no ESCA, we know that this did not happen. So the objectives we set relating to this question are to evaluate relevant past and current studies on meltwater interactions with ice, to prepare, train, validate, and test high-resolution imagery data for convolutional neural network modeling to address the issues of data randomness in training, validation, and testing. And that's very important, objective number 3. As I said earlier, the most important thing in doing all this is replicability, being able, the model being able to be applied to similar circumstances on which it was never trained. So objective number 4 be to evaluate extracted features against real images, and in the end also to highlight paths for interdisciplinary research in addressing global challenges. So responding to that question and fulfillment of these objectives are based on the planning of thousands of ESCA positive and negative, said 37,000 images. And right, so here we have examples of ESCAs. These are the images of ESCAs. I think sorry, got to get to the point. Oh, come on. Right, okay. These are the positive ESCAs, thousands and thousands of them. And probably those who are familiar with machine learning, if you look at these ones and you look at the negative ESCAs here, you probably start getting a feeling that there is a difference. I mean, these ones look quite smooth, and these ones, ESCA positives, look a bit roughy and But okay, so the method. I'm sharing this slide because it just provides an insight into what a CNN model is, what a convolutional neural network model is. Basically, it's based on the same mechanics as the standard neural networks, where you've got inputs, you've got weights, you've got biases, and you've got layers and neurons in between, and then you've got an output. The mechanics of CNN modeling, the simplest way, probably this is what I usually say to my undergrad students, that you can think of a simple regression model where you've got the relationship between Y and X, and as long as you know the gradient and the intercept, then of course you know the model. So I said earlier that we will be talking about the SMA algorithm, which seeks to optimize the performance. Now, the layers, one of the, the data randomness, the layers, got to go back there, the data randomness, the architecture of the network, they all have an impact on the outcomes of your analysis. So this is a standard structure of a convolutional neural network, which looks very similar to the standard artificial neural network, which I've just shared with you a while ago. And because, as I said, the weights play crucial role in giving us the output from the network. And the different layers, the pooling, the flattening, as shown here. Now, again, one key aspect of CNN is the kernel. Now, if you look at this one here, we've got 3x3 kernel. So this could be a 2x2. It could be a 4x4. The stride could be 1. It could be 2. It could be, and all those do have an impact on the outcome of the CNN model. So basically, what happens is that in this case here, I'm running a 3x3, one stride, that stride at a time. So it's creating for each convolution, and this can vary, and we need to pay attention to the impact which it brings to the outcome. So what do we do next? What do we do next is that we take the ESCA data, so the paleo ice sheet data, some of which are ESCA positive and some of which are ESCA negative, and we feed them into a CNN model, which is basically image analysis. And at some point, we're going to get the outcome, which tells us, okay, this image, sorry, let me say that again. We're training the model by showing it examples of ESCA positives and ESCA negatives. And through the process of training and validation, we get the accuracy of that of the model, which shows the positives and negatives. The next stage, of course, will be to test the performance of that model, where we take an unlabeled image, and we don't know whether it's ESCA positive or ESCA negative, and we feed it into the CNN model, and then we get an outcome. This is the most interesting part, because we want to see how good our model does. Yeah, so here are examples of ESCA positive and ESCA negative images as seen at different CNN model convolutions. On the left-hand side, we've got examples of ESCA positive and ESCA negative images are seen by, so here, the three images at the top. This is ESCA positive, so seen at different convolutions, you know, and this one is negative, again seen at the same level of convolution. And this is another example of ESCA positive and ESCA negative at different levels of convolution. Right, okay, so there we go. Here we, on this slide, we see the results of training and validation over 50 epochs. Now, what you see here is a performance of the training accuracy of just over 87%. And that of validation in black going over 90. To the right-hand side, that the training and validation loss, which basically derives from the same, you know, the same performance of this. So I'm going to pay attention to draw your attention to this one here. What you do if you carry on training, of course, which we do in the next slide, you're likely to see enhanced performance. But you know what could result is something called overfitting, and now overfitting happens when your data, your algorithm adapts so well to the data in such a way that it does consider even random noise as meaningful. Now, if you remember the two sets of images I showed you, they look very similar. So it's very likely that you could have some, you know, misclassified into one or the other class. And we want to avoid that scenario. Probably it's much easier said than done, because avoiding that amounts to being consistent or being optimal, which is a major challenge in machine learning. So this is training over 75 epochs. Sorry, I got to go back. 75 epochs, which actually so we've got the final results of this model were trained between 50 epochs and 75 epochs, but this one is based on 250 by 250 pixels. If you remember the 2 by 2 images I shared with you earlier, yeah, it is the higher the resolution or the lower the resolution will have a different impact on the outcomes of your results, and it's something that you really want to be aware of. So I'm going to spend more time on this one because this this is the sample measure assess algorithm I mentioned to you. We developed this algorithm a few years ago, and the first application was actually on structured data. It was developed for structured data, but we are using it on unstructured data here because it's because of its validity and universality. If you look at these mechanics carefully, it resembles bugging, those who are familiar with bugging in machine learning. But what it does is that it takes the sample, the data, like X. Now that for us will be the images which I showed you earlier in the two folders. And setting a learning model, which is a CNN in this case, we iterate by initializing parameters. Now, these parameters can be as different as the nature of the problem is. And I gave a few examples earlier on about having 250 by 250 or 100 by 100. The training images I showed you, the first one was actually 100 by 100. The next one, which was trained on 75 epochs, was on 250 by 250. So these are the variations which we need to, as we train the algorithm, try to memorize and come back and compare in very similar way as we do in cross-validation. Why do we do this? We do this because of something we call data randomness. It's randomness because we train the algorithm on training data. Now, training data is random data. We can have one set now, and the next time we pick another set is different. So it's that the nature of randomness we're talking about. We validate the model on a random data set, and we test it on a random data set. So as much as we're doing hypothesis testing, basic statistics, that we expect what we do to be representative of the general population. So that's basically what we did in here. And if I have to go back to these two training sessions, between them, the performance on previously unseen data was quite encouraging and very good. I'll bring this up in a minute. So these are the results of predictions, and we've tested this on hundreds of previously unseen images. So all you need to do is just read a new. Sorry, I had to put this 100 and 100, but one of them was actually 250. So previously unseen image and carry on predicting it using the weight, as I mentioned earlier, using the weight which has been memorized from the training. And basically what the algorithm does is that during the course of training, it does memorize the best performance. So if the performance does not improve, it doesn't keep that. So in the end, it finishes by giving you the best weight, set of weights, and the biases which it came up with, and of course, ignoring the rest. Now, and ultimately, you can use that to predict new classes, as we did here, and the performance on this was quite good. Not as high as in the training and the validating, I think, but the performance was over 82%, which is quite good. I tried to see if I can. Just confirm the, yeah, that's it. Yeah, okay, yeah, that was it. So 250. So the general performance was 82%, which is really encouraging. So this is still an ongoing work, and we still have an awful lot of work to do. So ultimately, we have highlighted the potential of machine learning in enhancing our understanding of they sub the processes which contribute to sea levels, and by automatically identifying eskers, we can quickly and easily map large areas of ice sheets beds. And we will be able to constrain the dimensions of subglacial meltwater channels quite significantly. So the morphometric information on esker size can be used to inform numerical models of ice sheet hydrology, which my colleague Robert knows more than I do, and I'm still learning from him, and which in turn can feed into models predicting future ice loss, and therefore give us an insight into understanding sea level rises. While CNN models can detect patterns that might go unnoticed by the human eye, for all their power and complexity, they do not provide thorough interpretation of the image data. It's because of that we need interdisciplinarity. We need to work in teams across disciplines to understand. I've started working with Robert on a few years, maybe going back three years or so. And before that, I knew very little. And it's quite amazing how much I think I understand now what happens in the Northern Hemisphere. So going forward, we have the following suggestions for the scientific community. There's no better way to view this bigger picture than through SDGs. We do need interdisciplinary approach to respond to new challenges and exploit new opportunities in sectors like manufacturing, agriculture, business, health, and education sectors that have been hit by the pandemic. So these applications can be extended to almost every sector. Tracking global variations and recovery strategies, and that will help us address real life issues like food security, productivity, and so on. The esker images we used in this paper are bare basics of deep and machine learning methods in glaciology and related fields. So we still, as I said, it's still ongoing work. We will need to explore further as a way of addressing climate change. And yeah, that's it from me. And I think I'm done with that. Thank you very much indeed for your attention.
Thank you very much, Kasim, for your very, very interesting and enlightening presentation. It involves quite a cutting edge artificial neural networks application. And this is applied to a very real world problem linking to Millennium Development Goals, amongst others. And we can certainly learn a lot from this application and its application to other areas besides eskers. So thank you very much. I am now calling for any questions or comments. If the audience attendees have any, please do submit these either through the Q&A facility or the chat facility. You're most welcome to do so if you would like to. So I'll give an opportunity for anybody to ask a question, make a comment, if there are any. Don't see any questions, no comments. So in this case, if there are no questions and comments, again, I would like to thank Dr. Mtondi for his presentation. Thank you very much. It's quite useful, I think, for us, and it also gives us a good indication of what kind of infrastructure resources we need to provide for researchers doing this kind of work. I do have a question, and perhaps I missed this during your presentation. In terms of data volumes, how much data are you, in terms of volumes, how much data are you using for this research work? That's my first question.
Okay, thank you, Anwar. We have 37,000 negative ESCAs, images which are ESCA negative, and we have over 1,041 ESCA positive images. So the positives probably aren't that many, but the negatives, actually they provided a very good learning information during the training, because we were able to swap the proportions of negative samples as we wished, but still 1,041 positive ESCAs was good, a very good sample. I'm sure because Robert still works in that area, there'll be more and more data to come, and we still expect to work with probably.
So the computing and the storage resources that you needed to conduct your neural network training, was this done on a conventional desktop or laptop? Did you use any high performance computing facilities for it?
Well, that's an interesting question. To get the images in the form that I showed you, which are basically, it's in pixels, 250 by 250. Robert had to use high performance computing. I don't know what that is. I'm sure if he's here, he probably can describe that, because he had to process the data before passing them on to me on a shared drive. So Robert, if you're here, and if they can unmute you, maybe you can help Anwar. Can you, Rudy, can you see Robert? Robert Storer. Well, he should be hearing me now, but if you can see him, and if you can unmute him, we will be able to provide.
Okay. While that is done, my last question, Kasim.
Yep.
The data that you've used, is it open? Is it accessible to anyone else who might want to use it, or how are there constraints on access?
No, there's no constraint on this data, much as I know, as long as, but I believe there will be, the university has the ODI, is signing up to the ODI, that's Open Data Initiative. So there is no, there's no constraint on the data, so we can actually make this data available to anybody who wants to. And myself, as a keen promoter of open science, which I've been for many years, I'm happy to even share the code, and anybody who is interested to apply the same, to actually produce the results of this one.
I have a question here from the audience, from the attendees. One question. Thank you for the interesting presentation, Professor. Are there any good first principle models of ESCA formation that could be used to generate additional data to supplement the measurements that you have?
That would have been a very good question to Robert to answer. I'm not sure I can answer that. First principle, sorry. The question is disappeared. What's happening?
Oh, sorry, I moved it. I'll repeat it if you'd like. The attendee would like to know whether there are any good first principle models of ESCA formation that could be used to generate additional data to supplement the measurements that you have.
Well, as I mentioned earlier in the presentation, ESCAs have been used previously in trying to understand, to relate them to sea level rises. So there are quite a lot of publications and the methods and techniques which were used before the high resolution dams came up. I'm not familiar with those. And I think my colleague Robert is teaching, but I don't see why we would like to supplement this through simulation. I think that's what this the question alludes to. But if we can, because the thousands and thousands of images we have are taken by drone aerial views. So we get these good data attributes in very high resolution. And so we can always get as many data attributes as we want. So it's probably, unless it's for experimental purposes, I wouldn't see why we would like to simulate the ESCA formation. Of course, there may be a reason why someone wants to simulate that, because these are historical, being unknown phenomena under the ice sheets. Maybe someone may want to simulate and see what might have been, but that's not an area I'm concerned with.
There's an interesting comment from a member of the audience, reading full Stokes finite element ice sheet / ice flow model, Elmer ice, I believe, could do this. And is probably develop models for ESCA formation. And there is a URL also given.
Well, I'm looking at that now.
Yes. So maybe that's also another take on the question, response to the question.
Yeah, I think that's quite helpful. I'm just looking at the text. But well, as I said, it's not an area I'm very familiar with. It's a shame Robert is not here. I think he must be teaching now. He's probably one who would have provided the best answer to this. I mean, that is the beauty of interdisciplinary. You see, it's one thing. Yeah, go on.
Sorry, Kasim. Another question from the chat. Is it possible to apply the same techniques for desert sandstone solutions, which are akin to the UAE, for example? I'm not quite sure. I don't know what you might know what UAE is, Kasim.
Well, I can only put together those two. Sandstorms in the UAE will probably mean desert and the United Arab Emirates. Yeah. Right. I think I've never thought about that, but I think the answer to that is yes. If sandstorms, because I've spent some time in that area and I know what sandstorms can do. So if we are to predict areas which are prone to sandstorms, then if we can take images of those areas and the images of areas which actually are not prone to that, and compare them in very similar way as we've done here, then I think the answer is yes. I mean, the purpose of binary classification, is not constrained to ESCAs or to ice sheets. As I said, it can be extended to any sector.
Yeah, I suspect it all depends on the imagery that one could get for particular application. In the case of desert sandstorms, what one would probably just need the correct kind of imagery for desert sandstorms, but I would venture to say that the application or the algorithm itself is probably more generally applicable.
I think it's true. Yeah, it looks very plausible that we can apply to desert storms. I mean, I've had a colleague from Japan who was talking about applying this to in oceanology. Predicting.
Thank you, Kasim. Thank you also for the audience for your attention and your participation. It's greatly appreciated. And we've got about 5 minutes left. If there are any last minute comments or questions, if not, then I would again like to thank you, Kasim. I hope this is not the last of your participation. And yeah, thank you for your time. And with that, I would like to conclude this session.
Thank you very much indeed, Anwar. I hope to see you soon. We'll probably see you tomorrow.
Okay. Well, and thank you.
Bye-bye.
Bye-bye.